Hello guys, welcome once more to another video in our YouTube channel. So in this video we look at radial and transverse motion of a particle, that is motion in 2 dimensions. So this topic is from further math mechanics, and the reference mock examination questions you are going to be looking at are already displayed to you. The Southwest Regional mock will be solved in the next video. If you want to watch part 1 of this radial and transverse motion of a particle, make sure you watch this video till the end. The part 1 video will appear at the end of this video and you can watch it. So in the part 1 video, for more information, I just solved these very mock examinations but for 2023. So this is part 2 where I'm solving 2024 for the very mock examination questions. So without wasting much of your time, let's get started with this video. Alright, so we begin with the Northwest Regional mock of 2024 question 7. The question reads, a particle P of mass m whose polar coordinate referred to an origin O at arrow theta moves along a plane curve under the action of a force F directed towards OP. The straight line OP rotates above O with angular speed theta dot. Theta dot is also omega. Now prove that r squared theta dot is equal to h, where h is a positive constant. Now if the magnitude of the force is mk on r squared, where k is a constant, show that r dot dot is equal to h squared on r cubed minus k on r squared. Also, at time t equal to 0, a particle is at a distance a from O and moving in the direction perpendicular to OP. Prove that at any later time, the radial component of the velocity of the particle is r dot squared equal to 1 on r minus 1 on a. All of that times 2k minus h squared into 1 on a plus 1 on r. Alright, so we are going to begin with proving that r squared theta dot is equal to h. Now, getting back to the equation, we have a particle whose mass is m, is moving along a curve under the action of a force directed towards OP. Okay, so first of all, I want you to visualize it in this way. If you are moving along a curve, then you have 2 components. Every vector has 2 components. It has a component in the radial direction and it has a component in the transverse direction. The radial direction is the direction of the curve, that is OP, okay, the direction of the line OP, and the transverse direction is a direction that is perpendicular to OP. So if I consider the force of P, the force will have the component in the radial direction, which is F_, and the component in the transverse direction, which is Ft. Also, if I consider the acceleration, then the acceleration will also have 2 components. The component in the radial direction, which is AR, and the component in the transverse direction, which is AT. Now, we have that the force, this particle was under the action of a force, and this force was directed towards OP. Now, if you are towards OP, then you are the radial direction, right? OP is actually the radial direction. So if the force is directed towards OP, it means that the transverse direction does not exist. So the force itself is just the radial, the force itself is just the force in the radial direction. And if you exist just in the radial direction, it means that your transverse component is 0. The transverse component is a component that is perpendicular to the radial component. It's like it is like the I and J component. The I component and the J component are perpendicular. Okay, so now how do I get the transverse component of the force? The transverse component of the force is the mass times the transverse acceleration. We know that F is equal to ma, but since you are specifying that the F involved is a transverse component of the force, then we need to take the mass times the transverse component of the acceleration and we equate to 0, since the particle was under the action of a force directed towards OP. Now, what is the transverse component of the acceleration? The transverse component of the acceleration has 2 different definitions. You can verify your formula booklet, and I'm going to give you the definition we are going to be using today. So basically, the transverse component of the acceleration is given by 1/r times the derivative with respect to time of r squared theta dot. That is a formal definition. Now if we actually undergo the differentiation process and we simplify, we are going to get the other definition as 2r dot theta dot plus r theta dot dot. But if you check the proof, the proof wants us to prove that the question wants us to prove that r squared theta dot is equal to h. So it therefore means that we are going to use this property. That is, you are going to use this definition, which is 1 over r d of r squared theta dot by dt. Okay, that's what we are going to use. In some other cases, depending on the question, we are going to use the second definition. But in this question, since we can identify r squared theta dot already, then we are going to use the first definition. Okay, so if I want to get the mass times the transverse acceleration and equate to 0, it therefore means I just need to take the mass times the transverse acceleration we have here and we equate to 0. Since the mass is a constant and it cannot be 0, and also r cannot also be equal to 0, then we can multiply by r and we divide by the mass, and doing that we just have d by dt of r squared theta dot equal to 0. Now this looks like a first order differential equation where we can separate variables and integrate. So doing that, I'm going to multiply both sides by dt, and then I have already separated the variables, so I need to integrate the left hand side and I integrate the right hand side. Now if I integrate the derivative of something, I just get that thing, because differentiation and integration are reverse processes. Okay, so if I integrate a derivative of a function, I get a function, as well as if I differentiate the integral of a function, I get the function. So integrating the derivative of a function, we get a function itself. So in this case, we are going to get r squared theta dot. Now when I integrate 0, I get 0, but since it is an indefinite integral, then we need to add we need to take 0 plus a constant of integration, and we can now call that constant of integration h. All right, so it therefore means that we have proven that r squared theta dot is equal to h. The left hand side, when integrated, we are integrating d of something. The r squared theta dot is the derivative of r squared theta dot, and when we are integrating the derivative, we just get the r squared theta dot, right? Now when we integrate 0 dt, we still get 0, but since it is an indefinite integral, we need to add the constant of integration, and in this case, to make the constant of integration resemble the proof, then the constant of integration must be h, so that we get the proof directly. So we have proven the a part of the equation. Now let's move on to proving the b part of the equation, proving that the second derivative of r is h squared on r cubed minus k on r squared. So first of all, we have a condition to be able to prove this, and the condition is that the magnitude of the force is mk on r squared. Now we have seen that since the force was moving towards OP, then the transverse component is 0, which therefore means that the force is just the radial component, which is Fr. So with that said, if I take the magnitude on both sides, I will need to take the magnitude, which just gives me the Fr, right? But now since it was moving towards OP, then we need to attach a negative sign to it, because it's actually a resistive force. Okay, it's moving under the action of this force. Okay, so when we take the magnitude, we get the magnitude of Fr times the unit vector, and this I here is actually ER. Okay, it's a little mistake. I is ER, and if we take the magnitude of ER is a unit vector. That's a unit vector in the transverse direction, and the unit vector is a vector whose magnitude is 1. That's the definition of a unit vector. So when we take the magnitude, we just get the Fr itself. But we know that Fr is actually negative mk on r squared. Okay, the magnitude is mk on r squared, but the Fr itself is negative mk on r squared, because it was acting towards OP. So with that said, what do we have? We have that MAR, because Fr is the mass times the acceleration in the radial direction. So we take the mass times the acceleration in the radial direction, then we equate it to negative mk on r squared. Okay, the m's are going to cancel, and then we have the acceleration in the radial direction is r dot dot minus r theta dot squared. That's its own definition. We equate it to negative k on r squared Then what next? Since we are looking for arrow dot dot, we need to add arrow theta dot squared on both sides, and we get arrow dot dot to be equal to negative k on arrow squared plus arrow theta dot squared. Okay, so if you're liking, if you're enjoying the video, make sure you comment, you like, and also you share the video at the end of the video. Okay, now what is theta dot squared? Theta dot squared, if you check the first, we are going to have arrow squared theta dot to be equal to h, which means that theta dot is h on arrow squared. Okay, I am sorry that I don't have a laser. The laser has refused to activate itself, but theta dot squared can be gotten from the first proof. Theta dot is h on arrow squared, so the theta dot squared should be h on arrow squared, all that squared. Now once we simplify, we have h squared on arrow to the power 4, but arrow divided by arrow to the power 4 will definitely give us arrow cube. Okay, so I can, since the negative sign, I can rewrite this. Remember that negative k arrow squared plus arrow h squared on arrow to the power 4 can also be written as h squared on arrow cube, because once you take arrow on arrow to the power 4, you get arrow cube. So you have h squared on arrow cube, then minus the first term, which is k on arrow squared. Is that a proof? Yes, that is a proof. So we have successfully proven that arrow dot dot is equal to h squared on arrow cube minus k on arrow squared. Make sure you are following up with your pen, okay, and also solving together with me, so that if you're hooked somewhere and you watch the video, you perfectly understand and you perfectly get how I simplified my steps, because to make the video to be a little bit shorter, I am not supposed to include all the steps because it's going to make the slide to be too cumbersome. All right, so we are done. We are done with the second part of the proof. Okay, so the last part of this question, at time t equal to 0, the particle is at a distance a from O and moving in a direction perpendicular to OP. C, we need to prove that at any later time, the radial component of the velocity of the particle is given by this. Okay, so first of all, we start by defining the velocity. The velocity has two components: the component in the radial direction, which is along OP, and a component in the transverse direction. And we are actually required to prove that the radial component is equal to something. Okay, and the radial component of the velocity is arrow dot. Okay, and the transverse component is arrow theta dot, but we are interested in arrow dot. We don't care about the transverse component. We are interested in the radial component. Okay, now we have that arrow dot dot is actually equal to the arrow dot by dt. Okay, that is, if you want to differentiate, so this is arrow dot dot. If the other dot is not clear, if you want to differentiate, if you want to get arrow dot dot, you can simply go by differentiating arrow dot with respect to t. Okay, and in this case, look at it keenly. You realize that from the previous question, our arrow dot dot is in terms of arrow, it's not in terms of t. So I need to get a similar expression of arrow dot dot in terms of arrow, that is in terms of the arrow, so that I can have a differential equation where I can separate variables and integrate. Okay, so let's start developing. We know that arrow dot is equal to the arrow by dt, right? So it means that dt is equal to the arrow divided by arrow dot. I'm going to replace the dt where I have dt here. So my dt is the arrow on arrow dot, but this dt is in the denominator, so I can reciprocate both sides. Once I reciprocate, I'm going to instead have 1 over dt. I'm going to reciprocate the arrow on arrow dot to have arrow dot on the arrow. Now I will multiply both sides by the arrow dot, and here on the left hand side I will have the arrow dot divided by dt. On the right hand side I will have arrow dot the arrow dot divided by the arrow, which therefore means that the left hand side is clearly arrow dot dot, and the right hand side we can rewrite it as arrow dot the arrow dot by the arrow. Now we can now go with this formula. So if I separate variables and I integrate both sides, okay, separating variables means taking everything in terms of arrow on one side and everything in terms of arrow dot on one side. So I'm going to take the arrow to the left hand side because my arrow dot dot from the previous question is in terms of arrow. Okay, so I have arrow dot dot the arrow to be equal to arrow dot the arrow dot. So I now integrate both sides. I need to integrate arrow dot dot the arrow, and I also integrate arrow dot the arrow dot. Okay, now doing that, you realize that if I integrating arrow dot dot is just equivalent to integrating my previous proof. My arrow dot dot was h squared on arrow cube minus k on arrow squared. You see, we can easily integrate with respect to arrow since h and k are constants. Now, when I integrate arrow dot the arrow dot, is basic. It's like integrating x dx, right? Because the arrow dot is there, and then you're integrating arrow dot with respect to arrow dot. It's like integrating x with respect to x. So normally we just need to have what? X squared divided by 2. So in this case, you are going to have this integral to be, now I'm going to try to simplify the right hand side by taking all the denominators to the numerators and negating their powers so that we can easily integrate. Now when you integrate the left hand side, clearly we have arrow dot squared divided by 2. Now when you integrate h squared arrow to the minus 3 the arrow, you get the first term here. That's the power rule. You just need to add 1 to negative 3 and you divide it by adding 1 to negative 3. Adding 1 to negative 3, you get negative 2, and you also divide by the negative 2. The same thing for arrow to the negative 2. K is a constant, so you just allow it there. You need to add 1 to negative 2, and you also divide it by negative 2 plus 1. Then since it's an indefinite integral, you need to add a constant of integration. Okay, so if I bring back those things back, if I send them back to the denominator, okay, because it's not good to be having arrow to the negative 2. It's better we send it to the denominator. Sending it to the denominator, we basically have this. Now we need to use the initial conditions to get the value of the constant of integration. And the initial condition is clear. It is saying that when a time is 0, the particle is at a distance of a from O, and it is moving in a direction perpendicular to OP. Now, if you are moving in a direction that is perpendicular to OP, it therefore means that your velocity will have only the transverse component, which means that the radial component of the velocity is 0. Remember that if you are moving along OP, if you are moving in the direction that is parallel to OP, then that direction is your radial direction, that is along your radius. Okay, now if the direction you are moving is now perpendicular to OP, it means that it is perpendicular to the radius. It therefore means it is the transverse direction. So if you're moving in a direction that is perpendicular to OP, then you are basically moving in the transverse direction. And when you are moving in the transverse direction, then the only velocity component that counts is the velocity component of the transverse direction, which means that the velocity component of the radial direction is 0. And we know that the velocity component of the radial direction is just arrow dot. Okay, so we can create a little table having when time is 0, the distance is arrow, which is equal to a, and the velocity is just the radial velocity, and that radial velocity is 0. Okay, no, the velocity is the transverse velocity, sorry, so it's supposed to be t here, or we can say the radial velocity is 0, so this is supposed to be t, and then we have here theta. Okay, voila, e of theta. Okay, so from there now we just need to replace the arrow dot. Remember here we need to replace, we need to find c. So to find c, we need to come here and we replace the arrow dot here with 0, because arrow dot is the velocity in the radial direction and it is 0 since you are moving only in the transverse direction. When we replace it with 0 and we square, we divide by 2, we still get 0. Now we need to replace arrow with a, okay, and then we need to find c by just adding h squared on 2a squared on both sides and subtracting k on a, and we get our c to be h squared divided by 2a squared minus k divided by a. Alright, so having c to be that, we can now replace c back into the general formula we had. This is it in the yellow coloration, and we have arrow squared divided by 2 to be equal to all of this. Now since we are looking for arrow squared, we multiply every term by 2. If we multiply the left hand side by 2, we are just going to have r squared. Now we need to multiply every term in the right hand side by 2. Okay, once we multiply, we have what I've displayed to you. Now I will try to bring all the terms in h together and all the terms in k together. If I bring all the terms in h together, I have this, and also all the terms in k together, I also have this. Now from there, since h squared and k are common factors in the first two terms and in the third and fourth term, then we are going to factorize h squared, or in fact we are going to factorize negative h squared. Once we factorize negative h squared, the first term will be left with positive 1 over r squared. But in the next term, to factorize a negative sign from a positive sign, we are going to be left with a negative sign, because to get a positive sign we need to combine two negative signs. All right, and once we factorize the negative h squared, we are going to get negative 1 over a squared. Now from these other two terms, I need to factorize 2k. Once I factorize from the first term, I get 1 on r, and I factorize from the second term, I get negative 1 on a. Now we need to apply the principle of the difference of two squares. Okay, because the difference of two squares is very applied here, because we have 1 divided by r squared minus 1 divided by a squared. Those are two squares that we are subtracting. So the difference of two squares says that a squared minus b squared is a plus b times a minus b. My a here is 1 over r, and my b is 1 over a. Okay, so from there we just have, if we factorize 1 on r minus 1 on a, or basically if you write this as difference of two squares before factorizing, 1 on r squared minus 1 on a squared is 1 on r minus 1 on a times 1 on r plus 1 on a. Then we now need to factorize 1 on r minus 1 on a, since it is common in both terms. Alright, so basically we have this, and factorizing 1 on r minus 1 on a, we are going to be left with, from the first term we are going to have negative h squared times the 1 on r plus 1 on a, and in the next term, this portion is not supposed to be there. Okay, it's a little error, this portion is not there again. All right, so everything just ends here. Yes, everything just ends here. So sorry for the error, it's not really easy to prepare a video, so let me indicate a portion which is not required. So this portion is not there. All right, and from there we can just interchange, right? Oh, again I still indicated a portion. So please guys, the proof is out, but we need to take note that this portion is not there. All right, we need to take note that that portion is not there. So we just need to interchange the positions of minus h squared times 1 plus r plus 1 on a and 2k, so that the proof will come out. So I think with this the proof is out and we are done with that question. Okay, so we move on to the second mock examination we have for today, the Bamenda Archdiocesan mock 2024 question 5. So it reads, a particle P moving in a plane has polar coordinates arrow theta referred to a fixed pole O and a fixed initial line in the plane. The radial and transverse components of the velocity of P at time t are lambda tan theta on 2 and lambda respectively, where lambda is a positive constant. Given that P is initially at the point A0, show that we have three things to show. So without wasting much of the time, let's get started with the first part. Okay, so we need to show that 1 over r, the r and the theta is equal to tan theta divided by 2. So first of all, they have given us the radial component of the velocity, and they have given us the transverse component of the velocity. The radial component is lambda tan theta on 2, and the transverse component is just lambda, and lambda is a constant. So previously we have seen that the velocity will be expressed in terms of its radial and its transverse components, and the radial component is r dot, while the transverse component is r theta dot. So we just need to equate r dot to what has been given. R dot is a radial component, it was lambda tan theta on 2, and the transverse component is arrow theta dot, and it is equal to lambda. Now, what do we know about arrow dot? Arrow dot is actually equal to the arrow by dt. Okay, so the arrow by dt will give us lambda tan theta divided by 2. But we also know that the arrow by dt is the same as the arrow by d theta times d theta by dt by the chain rule. The d thetas can still cancel, and we are left with the arrow by dt. But we are introducing this chain rule because the arrow given to us is in terms of theta, so we can easily differentiate arrow with respect to theta. Okay, since it's not in terms of t, that's why we need to use a chain rule. So the arrow by d theta again is the arrow by dt again is the arrow by d theta times d theta by dt. But what do we know about d theta by dt? D theta by dt is theta dot. Okay, and theta dot, we can get it from the transverse component of the velocity. Theta dot is just lambda divided by arrow. Anyways, from there, the arrow by d theta, in the place of theta dot, we replace it with lambda divided by arrow. If we find theta dot from this equation, we are going to get the value of theta dot as lambda divided by arrow. So we have to take the arrow by d theta times lambda on arrow for theta dot, and then we equate it to lambda tan theta on 2. Now we divide both sides by lambda, and then we are going to have 1 over arrow, the arrow by d theta, to be equal to tan theta divided by 2, because this lambda is going to cancel with this lambda. The two lambdas are going to cancel. Alright, so we are done with the first part. Now the second part, we need to show that arrow is equal to a sec squared theta divided by 2. So from the previous question, we just have to separate variables and integrate, because that's a first order differential equation, okay, in terms of arrow and theta only. So having the arrow, we just have to kind of cross multiply with the theta, so that theta should meet everything that concerns it on the right hand side. So doing this, we can perfectly integrate both sides. Okay, when I integrate the arrow on arrow, I basically have the ln of arrow, and when I integrate tan theta on 2, we can use a substitution u equal to cos theta on 2. Remember that tan theta on 2 is sin theta on 2 divided by cos theta on 2. So if I use this substitution, I'm going to come to this answer as negative 2 the ln of cos theta on 2 plus a constant of integration. Now we need to find that constant of integration using the initial conditions, and the initial condition is that the particle is initially at the point a0, which means that when arrow is a, theta is equal to 0. Alright, that's the meaning of you are at the point arrow 0 initially. So I need to replace arrow with a, okay, and I replace theta with 0, and doing that, I'm going to get k to be equal to ln a. Alright, we are going, because ln 0 is 1, sorry, cos 0 is 1, ln 1 is 0, so everything times negative 2 is 0, so ln a will be equal to k. Now we replace back the k into into the ln arrow formula, and we have ln arrow to be equal to, now remember that cos, come back here, the cosine of theta on 2, if I raise it to the negative 2, is the same as, because from the law of logarithm, I can carry this negative 2 and I give it to the power to cos. I put it as a power of cos, and we know that cosine to the negative 1 is 1 over sec. Okay, no, cosine to the negative 1 is sec because it is 1 over cos. So cosine to the negative 2 will be 1 over cos squared, which is sec squared. But the angle here is theta on 2. Now our k is ln 2, so that's what we have. Now from there, from the law of logarithm, since you are adding two logarithms that have the same base, the base is e, because ln is the same as log to the base e. They have the same base, so we just need to multiply what is inside the logarithms, that's the arguments. So I multiply a with sec squared theta divided by 2. Now since I am having ln arrow to be equal to the ln of a sec squared theta on 2, by default the arrow itself will be a sec squared theta divided by 2, and we have proven the second part. Now we need to prove the third part of the equation, which is proving that the acceleration in the transverse, in the radial direction, is negative lambda squared divided by 2a squared cos theta. So that's what we need to prove. So basically the acceleration in the radial direction is arrow dot dot minus arrow theta dot squared. That's the acceleration in the radial direction. So all we need to do is we find the missing terms, okay, and we plug it back into the acceleration. I will simplify to get the proof. So we have that r root dot is equal to lambda tan theta on 2, okay, which means that to get r root dot dot, I need to differentiate r root dot with respect to time. But since r root dot is in terms of theta, we need to use a chain rule where we are going to differentiate actually with respect to theta, and then alright, so sorry for I braked, so I don't actually know where I ended. But anyways, this is r root dot dot, we have r root dot dot, right? Alright, to get r root dot dot, like I said previously, we have to differentiate r root dot with respect to time. But because r root dot is not a function of time, we need to use a chain rule where we differentiate r root dot with respect to theta, and then we multiply it with d theta by dt. And d theta by dt is theta dot. So once I differentiate lambda tan theta on 2, to differentiate tan of theta on 2, we start by differentiating the angle. When we differentiate theta on 2, we get half, okay. Now we multiply it with the secant squared of the angle, because when you differentiate the tangent, you have sec squared. Now there was a lambda there, and then since we are differentiating with respect to time, we need to add theta dot. Alright, since the r root dot here was in terms of theta. Okay, so from there we know what we know. So let's just simplify. Now let us replace r root dot dot with what we have. Okay, remember that this theta dot here is the same as lambda divided by r. So when I replace theta dot with lambda divided by r, I will need to multiply it with lambda divided by 2. And when I do that, I am going to have lambda squared divided by 2r, then times sec squared theta on 2, minus this r remains. Now in the place of theta dot squared, we replace theta dot with lambda divided by r, but we have to square. So make sure in this instant you actually write down something so that you understand basically how I was able to simplify and arrive at this step. Okay, so previously we have seen that the radial component of the acceleration is this. So if you want to simplify, okay, now you realize that sec squared theta divided by 2 can be gotten from this proof. Sec squared theta divided by 2 is r divided by a, and we just have to replace the sec squared theta divided by 2 with r divided by a. Once we replace, this is a replacement. Now we now have the lambda squared on 2r still there, okay. Now the next thing to do is we have to simplify this whole bunch here, and when we do that, we are going to have lambda squared on r. So I hope you are following up the simplifications. Okay, now after doing this, we just have to simplify, okay, and noting very well that lambda squared divided by r, this r here is actually a sec squared theta. All right, so lambda squared divided by r will be the same as this is the r in the denominator. The r here is a sec squared theta. So when we divide, we basically have lambda squared divided by a sec squared theta. So hope you're following up. Now from there, now we just have to replace, right? And we know that 1 over sec squared theta is cos squared theta. In fact, it's theta on 2. So we are going to have lambda squared on a. Now 1 over sec squared is cos squared, right? So that's what that is where we are. Now we need to use some basic trigonometry identities to be able to come out with a proof. So let's go. Okay, previously we had that AR is equal to this, so you can factorize lambda squared divided by a. From the first term, you'll be left with half. From the second term, you'll be left with cos squared theta on 2. You can multiply, you can look for the LCM, right? Yes, you look for the LCM, and you factorize the 2 in the, as because 2 is the LCM, and you're going to have lambda squared on 2a times 1 minus 2 cos squared theta on 2. Now let me recall some trigonometry identities. First of all, cos 2 theta is 2 cos squared theta minus 1, which means that if I multiply all through by negative, I get negative cos 2 theta to be, I just need to switch, and I have 1 minus 2 cos squared theta. Now to get cos theta, basically I need to have the angle, okay? So I'll take 2 theta on 2 as well. I'm going to take theta on 2. It does not change anything. Now from there, what do I need to do? I need to multiply both sides by lambda squared on 2a. What am I doing? Why am I doing so? I'm doing so I should get my radial component of the acceleration. So once I multiply the left hand side by lambda squared on 2a, I also need to multiply the right hand side by lambda squared on 2a. Now doing that, you realize that the right hand side, the function in the right hand side is just basically our radial component of the acceleration. This is what we had. Alright, it therefore means that the radial component of the acceleration is negative lambda squared divided by 2a times the cosine of theta. Okay guys, I think we have come to the end of this video. So upcoming, we have the Southwest Regional Mock 2024 question 5. Still on the very topic, make sure you come back to the channel. Make sure you come back to the channel and you watch the video. Like the video, share the video with your friends, and don't forget to subscribe. Thank you once more for watching, and see you in the next video.